Okay, in this video we're going to get to the second bullet point here. These are the equations of the quadratic type. So many trigonometric equations are of a quadratic type, and that's something times something squared plus another number times something plus c equals 0. And here's a couple examples. In terms of sine x, we had 2 sine squared minus sine minus 1 equals 0, or 2 times something squared minus something minus 1 equals 0. And here's another one in terms of secant. The x's have just been replaced with trig functions. To solve equations of this type, factor the quadratic, or if it's possible, use the quadratic formula. So I'm looking at this first one. It's 2 sine squared minus sine x minus 1 equals 0. If looking at the trig functions confuse you, just replace it with x's instead of the sine. And this is minus 1x, or just minus x, minus 1. How does that factor down? So 2x squared, the only way to get that is 2x times x. And we have a 1, so our last term is going to be 1 times 1 is 1. And we just want to make sure when we add we get a negative, and when we multiply we get a negative. So these are going to be different signs. And the negative is the more powerful. So the 2 times this will probably be a negative 1, making this a positive 1. So let's see if I FOIL that out. Yes, I do get back to where I started. And now I can sort of put this back in terms of sign, and I'm going to set each factor separately equal to 0. So here on the left, I'm going to have 2 sine x plus 1 equals 0. And on the right, sine x minus 1 equals 0. And then I'll solve for sine. Subtract 1 from each side. 2 sine x equals negative 1. Divide by 2. Sine x equals a half. And on this side, it's one step. Just add 1 to both sides. The sine of x equals positive 1. And here's a unit circle. Let's look here on the left first. Where does... and this should be, yeah, that's right, it's a negative half. We subtracted 1 from each side. So there is a negative there. Where does sine x equal negative a half? Sine is our y coordinates, so we are going to be down here. So that occurs at 11/6 pi and 7/6 pi. 11/6 and 7/6. 11/6 and 7/6 pi. Now, should we write the plus 2 pi in after it? We don't have to on this problem because it says find all the solutions on this given interval from 0 to 2 pi. And there's only these two solutions. Our other possibility was here at sine of x equals 1. Well, where does that occur? It's a positive y value. That only happens once, and that's right up here at the top of the unit circle at pi over 2 radians. So x equals pi over 2. And there are all three solutions to that quadratic type trig equation. In example 5, before we do anything, we're going to have to rewrite in terms of a single trig function. If we read our equation, we have 2 sine squared plus 3 cos x. And we have differing trig functions. That's like x's and y's. We couldn't factor 2x squared plus y minus 3 equals 0 because the x's and y's are different. But we do have a Pythagorean identity. We can replace this sine squared with 1 minus cos squared. 2 times the quantity, 1 minus cos squared x. So that took care of the sine squared, and then here we'll have a plus 3 cos x and a minus 3 equals 0. So we distribute the 2 to those two terms. So we'll have 2 minus 2 cos squared x plus 3 cos x minus 3 equals 0. And then we collect our like terms. We have a 2 and a minus 3, so that's going to add up to negative 1. Minus 2 cos squared of x plus 3 cos x minus 1 equals 0. Now I don't like my leading term to be negative, so I can sort of block this off and multiply through everything by a negative, and I will also multiply this side by a negative, and sine or 0 is neither positive nor negative, so it's not going to do anything to the right side. distribute my negative, and now I'll have 2 cos squared of x minus 3 cos x plus 1 equals 0. And now I'm ready to factor. So I'll break this up into 2 factors. My first term in each binomial is going to be a 2 cos x and a cos x. And we want to end with a positive 1, so it's going to be 1 times 1. Our middle term is negative, our final term is positive, so it's got to be minus and minus. And now we set each of these independently equal to 0. 2 cos x minus 1 equals 0. Add 1 to each side. 2 cos x equals 1. Divide by 2, cos of x equals 1/2. And here on the other side, one step here, cos x minus 1 equals 0. Add 1 to both sides. Cos x equals 1. And where do these occur on the unit circle? Where does cosine equal positive 1/2? Again, cosines are x coordinates. So that's going to happen at 1/3 pi and at 5/3 pi. So 1/3 and 5/3 pi. And they did not restrict our interval like that previous example. It restricted from 0 to 2 pi. Here there is no restriction, so we have to do our plus 2 pi m. And also for the 5/3 pi. Now on to the other factor. Where does cosine equal positive 1? Well, that's our x coordinate. It only occurs one spot, right here at 0 or at 2 pi. So you know we will start at 0 plus every 2 pi after that times some integer n. Example 6, it says square and convert to a quadratic type. Right now we just have cos x plus 1 equals sine x, and our interval is 1 lap around the unit circle. What we have right now we cannot do much with, but we have a strategy where we have to do it, of course, to both sides. I'm going to take the left-hand side and square it, and I will also take the right-hand side and square it. So if we FOIL this out, cos x plus 1 times cos x plus 1 is going to be cos squared of x plus 2 cos of x plus 1 equals sine squared. And we can replace sine squared with a Pythagorean identity, 1 minus cos squared. And now everything is in terms of cosine. So let's get everything on the left and set it equal to 0. We're going to add a cos squared to each side. So we're going to add a cos squared here. And we're also going to minus 1 from each side. And we're going to minus 1 from this side. So cos squared plus cos squared are 2 cosines squared of x plus 2 cos x. 1 and negative 1 will cancel out. So right now we're equal to 0. And we can factor this side out a little bit. We have common terms. We can factor out a 2, and we can factor out a cos. So we're going to be left with cosine of x plus 1 equals 0. And we got 2 factors set equal to 0, so we will set each factor independently equal to 0. So first is 2 cos squared of x equals 0. Divide by 2. Cos squared of x equals 0. Take the square root. Cos of x equals 0. And we have our other factor. Cos of x plus 1 equals 0. Subtract 1 from each side, and we get the cos of x equals negative 1. So where do these occur? On the left, where does cosine equal 0? That's at half pi and at 3/2 pi. So this occurs at x equals half pi and x equals 3/2 pi. And our interval is restricted from 0 to 2 pi, so we don't have to add any plus pi ends after that. Now here on the other side, where does the cosine of x equal -1? Well, that's going to occur at one spot, at pi. X equals pi. So there's our three solutions. Are they all correct? We have to remember when we did algebraic techniques like this before, when we squared both sides of an equation, we could sometimes create extraneous solutions. So we have to check our solutions to make sure none are extraneous. And to do that, remember, we just want to plug them back into the original equation to see if they're true or not. Oops. So our original equation is cos of x plus 1 equals sine x. Cos of our solution plus 1 should equal the sine of that same solution. So let's see. When we plug in a half pi, what do we get? The cos of a half pi, cosine is 0, plus 1. Does that equal sine of a half pi? Sine of a half pi is equal to 1. So we get 1 equals 1. This one checks out. Oops. Pi over 2 is a good solution. Now let's check out 3/2 pi. Well, the cos at 3/2, cosine down here as 0, plus 1. The sine at 3/2 pi is -1. So does 1 equal -1? Absolutely not. This is an extraneous solution. Extraneous. We created that sort of out of thin air when we squared both sides of the equation in our first step. Finally, we have x equals pi. So here's our values at pi. The cosine value at pi is -1. -1 plus 1. Does that equal the sine value here is 0? Well, -1 plus 1 is 0. And 0 does equal 0. So this is another good solution. We had our one extraneous. 3 practice problems for you, modeling the 3 examples we just had. So the first one, you just factor it. Number 35, the second one, turn everything into tangent in terms of tangent. So, get rid of that secant squared, or you could get rid of the tangent and replace everything and make it all secant squared by using a Pythagorean identity. In number 37, you'll have to square both sides. So pause the video, try the problems, check your solutions. Okay, the first one is just a simple factoring. What times what is 2 cos squared? Well, that's a 2 cos x and a cos x. And we have our last term is 1, so 1 times 1 is 1. We want our middle term to be positive. So the 2, when we multiply it by the 1, we want that to be the positive piece, and this will be the negative. Now set each term equal to 0. 2 cos x minus 1 equals 0. So here the cos of x is positive 1/2, and cos x plus 1 equals 0 means cos of x equals -1. Where does that occur on the unit circle? Cosine is 1/2, that's our x value, so that's here at pi over 3, and also at down here at 5 pi over 3. So pi over 3 and 5 pi over 3. And because, this is we're equal to the positive 1/2, that'll be plus 2 pi n after, and plus 2 pi n. Laps around the unit circle. Now, where does cosine of x equal -1? That's only one spot right here at pi radians. So here our answer is, x equals pi radians plus 2 pi n. in number 35, we have to get everything in terms of one trig function. And I chose to get everything in terms of tangent. You don't have to do it this way. You know you should get the same solutions if you do all the steps right. So I'm going to take this secant squared, and I'm going to replace it with 1 plus tan squared. And then we have our plus tan squared x minus 3 equals 0. Distribute the 2. 2 plus 2 tan squared x plus another tan squared x minus 3 equals 0. So we can collect some tangent squareds. We have 3 of them. 2 plus 1, 3 tan squareds. And then we have a minus 3 and a plus 2, which is a minus 1. That's equal to 0. So, unlike the first one, it looks like here we're going to have to extract square roots. We only have one trig function, and it's a squared tangent function. So we're going to isolate that tan squared. We're going to add 1 to each side. 3 tan squared of x equals positive 1. Divide by 3. Tan squared of x equals a third. And then we're going to square root both sides. So our tangent of x is equal to plus or minus 1 over the root of 3. Or if we rationalize our denominator, plus or minus square root of 3 over 3. Now this occurs at 4 different places on the unit circle, and this is a lot like, this is going to be the same conclusion we got to in one of the earlier examples. Where does tangent equals square root of 3 over 3? Well, tangent is sine divided by cosine. A half divided by the square root of 3, or times its reciprocal. 2 over root 3, those would cancel. We would get 1 over root 3 like we had here. So that's going to occur at 4 spots. Pi over 6 radians. And it's going to occur at 5 pi over 6 radians. And again at 7 pi over 6. And one more time at 11 pi over 6. But remember, when we account for these, we could write plus 2 pi n after each of these, or from the 30 degree or pi over 6 radian angle, that will take us down here to the 7 pi over 6. So we can eliminate the 7 pi over 6 if we say plus pi n instead of 2 pi n. And from 5/6 down to 11 pi over 6, we can cancel that if we add just a plus pi n. Last one. And here I said the strategy is going to be to square both sides, but there is something we want to do first. If we square our left side right now, we'd have a cosecant squared, and then 2 cosecant times cotangents, and then a cotan squared. So we don't want to square it yet. We want to get something to the other side first. And when I did it, I chose to get the cotan to the other side. So here we have cosecant x equals 1 minus cotan x. And now we want to apply the strategy, square both sides. And here we'll have to FOIL. So on the left, we simply have cosecant squared of x, and then equal to 1 minus 2 cotans of x plus a cotan squared of x. The cosecant squared on the left here, we could replace with 1 plus cotan squared. So let's get out of there and write 1 plus cotan squared of x. So let's get everything on one side. I'm going to move everything to the left. So we're going to subtract this cotan squared. And we'll subtract this cotan squared. So those are gone. If we add 2 cotan of x to each side, and we're going to subtract 1, So we're going to add 2 cotan squared to the left. We'll have 2 cotan of x. And then we're subtracting 1. That will subtract this away. And we'll have this whole thing just left equal to 0. So we can divide by 2 and have the cotan of x equals 0. And let's remember one of our quotient identities. Cotan is cos over sine. Cos of x over sine of x. When does that equal 0? Well, that equals 0 when the numerator equals 0. If the denominator equals 0, of course, the world blows up. So we want to know when the numerator is equal to 0. When does cosine equal 0? Cosine are our x values, and that occurs at half pi and at 3/2 pi. So x equals half pi and also at x equals 3/2 pi. But we squared both sides. We possibly have created one of those solutions, and it will not work in the original problem. So we have cosecant plus cotan is 1, or we can do our reciprocals. 1 over the sine of our x value plus cotan is cos over sine, cos over sine of our x value. Does that equal 1? And the good thing here, at the x and y, or on the y-axis where these values occur, is we're either going to be plugging in 1s or 0s. So at a half pi, my sine value is 1. So here, that sine will be 1 over 1 plus sine, this will be a 1. The cosine at that value is a 0. So we get 1 divided by 1 plus 0 divided by 1, which is 1 plus 0, or 1. So pi over 2 checks out. Let's check 3 pi over 2. Still, our sine value, or our cosine value, is 0. So we're going to have 1 over something plus 0 over something. Our sine value here is -1. So this will be a -1 and another -1. So we have -1 plus 0 equals +1. That is an extraneous solution that we created when we squared both sides. So our only solution is at half pi. Homework for this section is just 4 problems.